Welcome to particulate model of matter, and in today's lesson we are going to look at diffusion and dissolving. So what are the things that we're going to learn? First, we're going to look at what is kinetic theory of matter and what it entails. Then we will look at the evidence for the kinetic theory of matter using one of the experiments which we can perform. Then we will look at what is diffusion and the definition of diffusion. Then we will move on to taking a look at another experiment in which we can use potassium permanganate 7 crystals to demonstrate diffusion in liquids. Then we will learn how to calculate the relative density of gases using relative molecular mass, which is also called the MR values of the gases. And then we will examine what's the relationship between the MR values and how it's related to the rate of diffusion of gases. So the lower the MR values, the gases are going to diffuse faster. So we're going to look at that. And then last we will look at what is the meaning of dissolving, and as we examine the process of dissolving. So those are the things that we're going to look at. So what is a particulate model of matter? Particulate model of matter, it lets us understand how the particles in matters are arranged, their packing, whether they are packed very close together or whether they are loosely packed, and the physical properties and behaviors such as density, speed of the particles, etc. So these are the things that we're going to look in a particulate model of matter. Before that, let's look at what is kinetic theory. Kinetic theory says a couple of things. Kinetic theory states that all matters are made up of particles. So whether it's a solid, liquid or gas, they are all made up of particles, and that these particles are in continuous motion due to the internal energy they possess. So the particles have their own energy with which they will move, and that energy is what we call as internal energy. So the particles will be in continuous motion. So if we can demonstrate that all matters are made of particles and particles are in continuous motion due to the internal energy without the motion or the movement being influenced by factors such as density, gravity and all that, then we have proved kinetic theory of matter. So what is diffusion? Diffusion is a process where particles actually move from a region of higher concentration to a region of lower concentration across a concentration gradient using the internal energy of the particles, and that is what we mean by diffusion. So you must remember the definition for diffusion. It's a process where the particles move from a region of higher concentration. It's always from a region where there is a huge number of such particles, that's what we call as a region of higher concentration, to a region of lower concentration where you can find less of that particle. And across a concentration gradient, of course, if you move from the higher concentration to lower concentration, there's a concentration gradient, and that is using the internal energy of the particles. So here is a example of a model of diffusion. So if you look on the left side of the model, you can actually see that here there is a huge number of particles. So we would call this region as the region of higher concentration. And on the right hand side of the model, we can see that there are fewer particles here, right, within the same volume. And this region is what we call as region of lower concentration. And of course, if we move from the region of higher concentration towards the region of lower concentration, there is a gradual decrease in the number of particles. So we call that as the concentration gradient. So the diffusion says that diffusion is a process where the particles would move from a region of higher concentration, which is on this side, towards the region of lower concentration, which is on the right hand side, across the concentration gradient. And this is entirely done using the internal energy of the particles. We do not have to heat, we do not have to do anything. The particles will just begin to move on its own from the higher concentration region to a lower concentration region. And this is the process called diffusion. And diffusion is the best way to, is the best evidence for the kinetic theory of matter, meaning to say that particles possess internal energy with which they move. So diffusion provides the best evidence for the existence of kinetic theory of matter. So we can formally demonstrate this in the laboratory, okay, using this experiment which I'm going to describe to you. The procedure is, first we're going to take 4 jars and fill 2 of the jars with nitrogen dioxide gas. The reason why we are choosing nitrogen dioxide gas is because it is brown in color, and since it is brown, it is visible, we can see it. And another 2 gas jars, okay, we can just simply fill it with air. Just leave it open and it will be filled with air. Okay, air is colorless. So like that. So we are going to fill up 2 of the jars with nitrogen dioxide gas, and another 2 we just leave it open so that the air will be filled up. So the second step is invert the jar of air over the jar of nitrogen dioxide like this. So we take the jar of air and we just put it on top of the jar with nitrogen dioxide, and we're going to do the same thing with the other setup. Set up a control experiment alongside, in which the jar of nitrogen dioxide is going to be inverted over the jar of air. Okay, of course you have to remove the lid on this before you actually put it on top, and then remove the lids and leave the setup undisturbed for about 15 minutes and take note of the changes observed. So what did you notice as soon as we remove the lids? So what we would see at the end of the experiment is the entire setup turns brown in color. Of course, not as intense as it was before, but the entire setup turns completely brownish. And what has caused this to happen? The observation would be both jars turns uniformly brown in color. And let's make the conclusion from this. Air, which is colorless, and nitrogen dioxide gas, which is brown in color, have completely mixed, okay, into each other using the internal energy. Okay, we did not have to heat, we did not have to do anything, we did not have to shake or whatever. We just left it open, and the gases have diffused into each other, okay, using entirely their internal energy. Nitrogen dioxide, though denser than air, still diffuse into the jar above it, which you can see from experiment 2, right? So the jar actually, the nitrogen dioxide, even though it's denser than air, it still diffuse into the jar above it. Neither the gravity nor the density influence the mixing. The reason why we did 2 setups is that some people might argue that the nitrogen dioxide actually came down. Okay, that's because it was denser compared to air, and that's the reason why it mixed, and not necessarily due to the internal energy. To counter argue that, we did one more setup. In that setup also, if we actually notice the same kind of observation, so it is the density or the gravity, it is neither the density nor the gravity actually influence the mixing. The mixing was entirely due to the internal energy. It is entirely due to the internal energy. These are the conclusions we can draw from this experiment. So this is how we provide or prove kinetic theory of matter. Let's look at another experiment in which we can take a look at how we can demonstrate diffusion in liquids. The procedures to follow will be, first we're going to take a beaker and just simply fill it with water. Then next we're going to take a potassium permanganate 7 crystals. Okay, so the reason why we are choosing potassium permanganate 7 crystals is that, one, it is purple in color, so it's easy to see. Okay, it will color the water, and okay, any place where the purple coloration spreads, we know that it is due to the potassium permanganate. And second reason is potassium permanganate 7 crystal is also soluble in water. So we're going to place the potassium permanganate 7 crystals into the water. Now instead of just simply dropping it, okay, in which case it will start to dissolve as soon as it touches the water, instead of doing that, we want it to actually gently go and settle down at the bottom and then start dissolving. So we make use of this glass tube, and we can just drop the potassium permanganate 7 crystal, and it can go right to the bottom of the beaker of water. Then observe the changes in the water. So if you look at the beaker of water, let's see what's going to happen. The observation would be potassium permanganate 7 crystals slowly dissolves in water, and the water slowly turns into a purplish solution. Okay, as you can see here, it will turn purple throughout. What can we conclude from this? The particles of potassium permanganate 7 crystals, okay, or particles of potassium permanganate 7 diffuses throughout the water using its internal energy, and likewise water has also been moving around using its own internal energy, and both of them have thoroughly mixed with one another, and that's the reason why the entire beaker of water turns purplish. Next, we'll look at how to determine the density of gases using MR values. MR value is a short form for relative molecular mass, okay, where we compare the molecular mass of a particular gas with respect to carbon 12. That's why the word relative molecular mass, okay, which we'll look at it much more in detail when we look at the topic on moles. The periodic table of elements can be used to calculate the relative molecular mass. For short form, we call it the MR value. The R stands for relative, then M stands for molecular mass, values of the gases for short. So let's say, for instance, if we take a look at nitrogen here, okay, beside each and every one of the elements, okay, look at lithium, you know, there is a 3 and a 7. Beside each of the elements, there are 2 numbers given, okay. So if you look beside lithium, you can see 3 and a 7. Beside beryllium, you can see 4 and a 9. Beside boron, you can see 5 and 11. Beside carbon, you can see 6 and 12. Beside nitrogen, you can see 7 and 14. There are 2 numbers given. So if you look at this, so you can see the 2 numbers. Now the top number is called the atomic number, okay. We don't have to look into it at this stage, okay. We will look at it when we actually look at the atomic structures later on. But now the number that I want you to pay particular attention to is this number, okay, the bigger number. The bigger number beside the element is called the relative atomic mass of the element, okay. Otherwise, it's also called the AR value, relative atomic mass or atomic number, okay. This value, relative atomic mass, okay, which is called the AR value. So it can be identified by looking at the 2 numbers, okay. Of course, some periodic table might print the 14 on top and 7 at the bottom. So in this case, this periodic table, okay, 7 is on top, 14 is at the bottom. So the easy way to identify, okay, the AR value is to look at the bigger number. But of course, you must remember there are some exceptions to this rule of bigger number, because if you look at hydrogen, it's a 1 and a 1. But looking generally at this periodic table, the bigger numbers are always written at the bottom. So the bottom number is actually the relative atomic mass. So for hydrogen, the relative atomic mass is also 1. So what we're going to do with this value? We can use these AR values to calculate the MR values of the gases, relative molecular mass of the gas, by using relative atomic mass of that particular element. So we need to know the molecular formula of the gas in order to determine what is the relative molecular mass. So in a while, I'm going to show you a few examples of how we can determine the MR values. Of course, the MR value will give us an indication of the relative density of the gases when we compare 2 or more gases. So here is an example. Calculate the MR value of nitrogen gas. Okay. So first, of course, the first thing is we have to look at the periodic table and identify nitrogen. So I have just pulled out the nitrogen here. So beside nitrogen, there is a 7 and a 14. And of course, the number we need to pay particular attention to is the bigger number, which is 14, which is also known as the atomic mass. So since nitrogen molecule, okay, it's a diatomic gas, it has 2 atoms of nitrogen. So the MR value when we want to calculate for nitrogen, N2, that means there are 2 atoms. Each atom has a relative atomic mass of 14. So we're going to take 2 of this, right? So we're going to take the 2 and multiply it by 14. So if you take 2 times 14, the relative molecular mass of nitrogen would be 28. So it's pretty simple, right? So how we can calculate the MR value for nitrogen gas? So let's look at another example. How about hydrogen gas? Okay, look through the periodic table and look at hydrogen. And when you see hydrogen has got 1, 1, okay? So the relative atomic mass is also 1, relative atomic number also 1 in this case. So do not worry about the relative atomic number, but relative atomic mass is 1. And just like nitrogen, hydrogen is also a diatomic gas. So since hydrogen molecule has 2 atoms of hydrogen and each of them have got the relative atomic mass of 1, the MR value for hydrogen would be, we take the 2 and we're going to multiply that by relative atomic mass of hydrogen, that's a 1. So we're going to take the 2 times a 1, the relative atomic mass of hydrogen is, relative molecular mass of hydrogen is 2. So if we were to just take a look at, nitrogen and hydrogen, and if we were to compare, okay, we can see that nitrogen has got a relative molecular mass of 28, while hydrogen has got a relative molecular mass of only 2. So from this we know that hydrogen is less dense while nitrogen is more dense, okay, because it has a higher MR value. Calculate the MR value for chlorine gas, Cl2. Okay, from the periodic table, the chlorine has got a relative atomic mass of 35.5, and chlorine is also a diatomic molecule. That means it comes as a package of a cluster of 2 atoms of chlorine atoms per molecule. So the MR value for chlorine would be, there are 2 atoms of chlorine per molecule. So we're going to take the 2 and we're going to multiply that by the relative atomic mass of chlorine, and that is of course 35.5. And when we multiply them together, so we get 2 times 35.5 giving us 71. Let's look at another example. Okay, calculate the MR value for oxygen gas. So from the periodic table, once again, oxygen, there are 2 numbers, which is one is 8, the other one is 16. Of course, 16 is the relative atomic mass. So since oxygen is also a diatomic molecule, it has 2 atoms of oxygen per molecule. So the MR value for oxygen would be, we're going to take, because there are 2 atoms, so we're going to take the 2 and we're going to multiply that by the relative molecular mass, relative atomic mass of oxygen, that's a 16. So twice of 16 is going to work out to 32. So now if we were to compare chlorine gas and oxygen gas, which one is denser? Of course we can see chlorine has got a molecular mass of 71, whereas oxygen has a relative molecular mass of only 32. So from this we know that chlorine is denser compared to oxygen. Let's go for a few more examples. Example 5. Here I am giving you a compound type of gas. Okay, a compound is made up of more than one type of element. Okay, carbon dioxide is made up of carbon atoms as well as oxygen atoms, but they are in the ratio of 1:2. There is 1 carbon and there are 2 oxygen. So from the periodic table we need to actually locate both of these elements, carbon as well as oxygen. Beside carbon, the number written, the atomic mass written is 12, and beside oxygen is a 16. But there is only 1 carbon, but there are 2 oxygen atoms per molecule. So since carbon dioxide molecule has 1 carbon atoms and 2 oxygen atoms, so the MR value for carbon dioxide would be, there is only 1 carbon, so we're just going to take just the 12, okay, due to the carbon, and we're going to add it to, there are 2 oxygen atoms. So each of the oxygen atom has got a relative, okay, atomic mass of 16. So we're going to take the 2 and we're going to multiply that by 16. So twice of 16 is of course a 32, and 32, if we add a 12 to it, 32 plus 12 is going to end up giving us 44. So this is the relative molecular mass of carbon dioxide is 44. How about if we take sulfur dioxide gas? Okay, 1 sulfur atom is bonded to 2 oxygen atoms. So we need to now look for in the periodic table, look for sulfur and the element oxygen. So since sulfur dioxide molecule has one sulfur atom attached to two oxygen atoms, so if we want to calculate the MR value for sulfur dioxide, due to the sulfur, okay, the relative atomic mass of sulfur is 32. So we're going to take 32, but of course it is 1, so we need not write 1 times 32, we can just write 32. But however, when we go to the oxygen, there are 2 atoms of oxygen per molecule. So we're going to take the 2 and we will multiply that by the relative atomic mass of oxygen, and that's a 16. So we're going to add a 32 to twice of 16. Twice of 16 is of course another 32. So we're going to take a 32 due to the sulfur plus twice of 16, which is another 32 due to the O2, okay, the couple of oxygen atoms, and 32 and a 32 is going to add up to 64. Therefore, the relative molecular mass of sulfur dioxide is 64. Now, once again, let's compare these two gases, okay, which one is denser? Okay, carbon dioxide has a relative molecular mass of 44, while sulfur dioxide has a relative molecular mass of 64. Obviously, sulfur dioxide is bigger, fatter, and clumsier. So this is, of course, much denser compared to carbon dioxide. Sulfur dioxide is much denser. Let's look at another example. In this case, okay, let's look at butane gas. Butane gas is made up of 4 carbon atoms bonded to 10 hydrogen atoms. So we need to, of course, look for carbon and hydrogen in the periodic table. So there we have carbon has got a relative atomic mass of 12, whereas hydrogen has a relative atomic mass of 1. But if you look at one molecule, there are 4 carbon but 10 hydrogens. So there are 4 carbon atoms and 10 hydrogen atoms, okay, clustered together to form a molecule of butane. So the butane's formula is therefore C4H10. So the MR value for C4H10, if we want to calculate, is there are 4 atoms of carbon. So we're going to take the 4 and we're going to multiply that by the relative atomic mass of carbon, that's a 12. So 4 times 12, that's going to become 48. That will be the mass due to carbon. And now for hydrogen, there are 10 hydrogen atoms. So we take the 10 and the relative atomic mass of hydrogen is a 1. So we're going to multiply that by 1. 10 times 1 is of course going to give us a 10. So 4 times 12 would be 48. Plus, due to the hydrogen, there is a 10 times 1, that's a 10, 48 plus a 10 is going to work out to 58 as the relative molecular mass of butane gas. How about another example, 8. Calculate the MR value for ethene, okay, the molecular formula here is carbon atoms 2 and hydrogen atoms 4, right? So 2 carbon atoms bonded together with 4 hydrogen atoms to form a molecule of ethene. So again in the periodic table we're going to just use the carbon and hydrogen to work out the relative molecular mass of ethene gas. So since ethene molecule has 2 carbon atoms and 4 hydrogen atoms, its MR value would be 2 carbon atoms. So each carbon atom has got a molecular mass of, relative atomic mass of 12. So twice of 12. And we're going to add it to 4 hydrogen atoms, okay. So there are 4 hydrogen atoms per molecule, so we take the 4 and we're going to multiply that by the relative atomic mass of hydrogen, that's a 1. So due to the carbon would be 2 times 12 and that's going to be of course 24, plus due to the hydrogen is 4 times 1, which is of course equals to 4. And if we add a 24 and a 4 together, that's going to work out to give us the MR value of 28 for ethene gas. So here, of course, we can see butane is much denser compared to ethene. Now, what's the purpose of learning about the MR values? Of course, the relative molecular mass would give us an indication of the rate of diffusion of the gases. The less dense gas, that means those with a lower MR value, would end up diffusing faster compared to a more dense gas. So how do you identify a more dense gas or a denser gas? Of course, it will have higher MR value. So let's look at that and understand with an example here. So I have given you a number of gases, okay? I have given you about 6 gases. Arrange the following gases from the highest rate of diffusion to the lowest rate of diffusion. Okay, that means the rate at which they are going to move from one place to another using their internal energy. And of course, in order for us to do that, we need to know what is the relative molecular mass for each and every one of the gases. So if we use the technique that we just learned, for nitrogen, the relative molecular mass would be 28. And when we look at the hydrogen, okay, hydrogen's atomic mass is 1, if you recall. So there are 2 atoms. So that should give us a 2. Sulfur dioxide, sulfur is a 32 and each oxygen is 16. So 2 oxygen is a 32 and a 32 together, making it to 64. And ammonia, nitrogen is 14, 3 hydrogen is 3, 14 and a 3 together is 17. And carbon monoxide is 1 carbon and 1 oxygen. So carbon is 12, oxygen is 16, 12 plus a 16 is 28. And carbon dioxide is 1 carbon to 2 oxygen. So twice of 16 is due to the oxygen, that would be 32 plus another 12 due to the carbon, and that should work out the MR value as 44. Now we have already worked out what are the MR values for each and every one of the gases. All that we need to do is now to arrange them, because the question says highest rate of diffusion to the lowest rate of diffusion. So we're going to arrange the least dense gas to the most dense gas. Now if you look at this list, so which gas is the least dense? Of course the one with the lowest MR value, and it is very obvious from the list of the MR values, hydrogen is the least dense gas. So we're going to write hydrogen followed by 17 MR ammonia, and nitrogen and carbon monoxide together, because both of them have a relative molecular mass of 28, and carbon dioxide has got a relative molecular mass of 44, and sulfur dioxide is the heaviest of all, so with a 64 as its MR value, and that is the most dense. So we have arranged the gases, okay, from the least dense or the lightest to the heaviest or the most dense gas. So of course if you look at the point which I mentioned earlier, less dense gases, that means those with the lower MR value, is the one that's going to diffuse the fastest compared to a more dense gas indicated by a higher MR value. So the least dense in this case is hydrogen, and hydrogen would have the highest rate of diffusion followed by ammonia, whereas nitrogen and carbon monoxide, both of them have a relative molecular mass of 28. So both of them going to diffuse at the equal rate because they are equally dense, and of course followed by carbon dioxide, and of course the slowest to diffuse, slowest to move around would have been sulfur dioxide in this list of gases. So sulfur dioxide will have the lowest rate of diffusion. So the example we wanted to arrange from highest rate of diffusion to the lowest rate of diffusion, there you have the list how they are arranged. Let's look at example 10. What happens to the water level at Y? Okay, here is water level here, when oxygen gas O2 is present inside the porous spot. Of course, oxygen is inside the porous spot, and outside the porous spot we have got hydrogen. And of course, you should know by now, hydrogen is the least dense of all the gases, because a relative atomic mass of hydrogen is just 1, and since it is a diatomic molecule, twice of 1, the MR value for hydrogen would be 2. And of course, we are going to compare this hydrogen with the oxygen. So we also need to work out what is the MR value for oxygen. Each oxygen is 16, and 2 oxygen would give us 32 as its MR value. Now that we have these two values, now which one of the gas is going to diffuse faster? Of course, the less dense gas is going to diffuse faster, right? So from this MR value, we can see that hydrogen is less dense compared to oxygen, which is of course more dense. And the less dense gas is going to diffuse in faster into the porous spot. So there's going to be more molecules of hydrogen getting into the porous spot. By the way, a porous spot is just a pot in which gaseous exchange can occur. Okay, there are pores around where the gases can just diffuse in and out. So inside the porous spot, we're going to get more hydrogen gas going into the porous spot, And oxygen being bigger, fatter, and clumsier, they are going to diffuse out, take their own sweet time, and they're going to diffuse out at a much slower rate. So what is this going to do to the water level? Of course, if there are more gases getting into the porous spot, the pressure inside the porous spot is going to increase. And when the pressure here is going to increase, what's going to happen is that this increase in pressure, or the gas molecules, are going to just come down and push this level of water on the left side of the limb. This is also called the manometer. And the right side, since it is open to atmosphere, the pressure on the right side is equal to the atmospheric pressure. So the gases here is going to just push it down on the left hand side of the limb. And of course the right hand side of the limb, where the Y is, the water level is going to rise. So the answer for this is water level at Y is going to increase or rise or go up. Let's look at another example. Example 11. What happens to the water level at Y, which is the same side, okay, on the right hand side of the limb? But this time, inside the porous spot, we have got ammonia gas, NH3, and chlorine gas, okay, which is going to be delivered by the delivery tube into the beaker, which is outside the porous spot. So, but of course, as you might say, as you might have already guessed, so we need to start off with the MR values for each of the gases. So chlorine, each chlorine is 35.5, and 2 chlorine would work out to 71. And if we look at ammonia gas, there is 1 nitrogen and 3 hydrogen. So the nitrogen has got a relative atomic mass of 14, and each of the hydrogen is 1. So 3 hydrogen is a 3. 14 plus 3 is going to give us 17. And we can see from the MR values of chlorine and ammonia, we can see that ammonia, which is NH3, is less dense. So, and chlorine gas is going to be more dense, and ammonia gas is going to be less dense. Of course, the less dense will diffuse faster compared to the more dense. So, chlorine is going to diffuse in much more slowly into the porous spot. So, chlorine is going to diffuse in much slower because it is MR value is 71, is so much heavier compared to ammonia. So, it's going to be very clumsy, and they're going to take their own sweet time to get into the porous spot. Whereas the ammonia gas, being less dense, is going to diffuse out much faster. You know, lots of molecules of ammonia is going to come out very quickly compared to the chlorine gases, which are going to take their own sweet time to get into the porous spot. And as a result, what's going to happen now is that there is going to be a decrease in the pressure inside the porous spot. And of course, if there is a decrease in pressure and the atmosphere is pushing down on this side, so this side, the water level is going to go up on the left hand side of the limb, and which subsequently is going to affect the water level on the right hand side of the limb, and that is going to drop, or that's going to fall. So the water level at Y is going to drop as a result of putting these two gases at their respective positions as indicated in the question. Okay, let's look at another question, example 12. There is HCl gas and ammonia gas. Okay, HCl is hydrogen chloride gas and ammonia gas. And what will happen is these two gases would react together to form a white solid. Okay, this is a gas, this is a gas. And of course, when they react together, they're going to form a white solid called ammonium chloride, okay, whose formula is NH4Cl. Now, how do we produce HCl gas and NH3 gas in this experimental setup? We will do it by a simple way. Cotton wools are dipped in concentrated hydrochloric acid, of course, a fuming acid. So if we take cotton wool and we just dip it into concentrated hydrochloric acid, so the fumes of hydrogen chloride gas is going to just start diffusing into the space here, right? And concentrated aqueous ammonia, which when we dip it in cotton wool, so the ammonia gas is just going to start diffusing out. Okay, and these two gases are going to just move towards each other, and where they meet, okay, where they react with each other, we are going to form an ammonium chloride, okay, white color solid, and that white color solid will deposit on the glass tube, so which would make it easier for us to actually see. So the question is asking what is the likely position of where the white powder would be formed, right? So let's say this is ammonia gas, NH3, right? And this side we have the HCl. But to determine the rate of diffusion, we need to know what is the MR value for each and every one of the gas. So for ammonia, the NH3, the relative molecular mass of ammonia is 17. And of course, on the right hand side, that's going to act as a source of hydrogen chloride gas. So we also need to work out the MR value, or the relative molecular mass. So chloride is 35.5 and hydrogen is a 1. 35.5 plus a 1 is going to give us 36.5. Now just by looking at these two MR values, we can conclude that ammonia is lighter and it is less dense. And of course, if it is less dense, it's going to diffuse much faster compared to hydrogen chloride, which is a fat molecule, which is going to move very clumsily and move very slowly. So of course, ammonia being lighter, it's going to diffuse faster. Okay, whereas hydrogen chloride is going to travel only a short distance because it's going to diffuse at a slower rate. So when ammonia and hydrogen chloride react together, of course we are supposed to get ammonium chloride gas. So therefore they are not going to meet in the middle, okay? They will meet somewhere towards where the hydrogen chloride is, and the likely position where ammonia is going to be formed, ammonium chloride is going to be formed, is at the position C. This is due to the difference in the relative molecular masses and hence the rate of diffusion of the two gases based on the relative molecular mass. Gaseous particles possess higher speed and the rate of diffusion is greatest in gases. So of course, if we were to compare solids, liquids and gases, the three states of matter, gases are going to move at the highest rate, okay? They are going to move the fastest, okay? So if we were to arrange gases, liquids and solids, the rate of diffusion is greatest, or highest rate of diffusion can be observed in gases, and the lowest rate of diffusion will be observed in solids, and of course liquids will have a slower rate compared to gases, okay? So gases, since they have complete freedom of movement and also due to the fact that they have a higher energy, so they're going to diffuse much faster, much more quickly. Next we will look at what is called dissolving. When particles of solutes, okay, usually solutes are substances which are smaller in quantity, get in between the spaces of the particles of the solvent, it is called dissolving, okay? We have got to remember this definition as well. When particles of solutes get in between the spaces of the particles of the solvents, it is called dissolving. Now imagine if I were to fill up a room entirely with basketballs, right? It's already filled to the brim, no more basketballs can be put into the room, okay? And all of a sudden I give you a bucket of marble and I say, can you please get this into the room, okay? One bucket of marbles. So do you think it will be able to get into the room still? Yes, of course you can do that, because the moment you pour the bucket of marble into the room, the marbles being smaller in size, they are going to get into the spaces between the basketballs, right? So even though we say the classroom is filled with basketball, we are still able to get in the marbles into the room because the marble particles can occupy the spaces between the basketballs. So that is exact replica of what is dissolving is. So when we take a solute such as copper sulfate and we add it to a solvent such as water, we are going to end up getting a solution. Okay, this is called copper 2 sulfate solution. So a solute plus a solvent makes up a solution. So for example, if we take sugar and we dissolve it in water, we're going to get sugar solution. And if we take acid and dissolve it in water, we get acidic solutions. And if we take salt and we dissolve it in water, we get salt solution. So this is how we make solutions and for you to form solution, of course we need to carry out the process of dissolving. And when we want to understand what is dissolving, it is basically, remember, solute particles getting in between the spaces of the solvent particles, okay? That's what we call as dissolving. So here is a particulate model of that. So if we were to imagine these as the solvent particles, and here you can see in between the solvent particles there are spaces, right? So in these spaces the solute particles can get in between these spaces. So when the solute particles get in between the spaces of the solvent particles, we call the process as dissolving, and this mixture of the solute and the solvent together we would call them as solution. Since solute particles, okay, these ones, the green color ones, get in between the spaces of the particles of the solvent, the total volume of the solution will be lesser than the sum of the volumes of the solutes and the solvent. If let's say if we take 50 cm cube of sugar and we try to dissolve it in 50 cm cube of water, we can't add 50 plus 50 and give us 100 cm cube of sugar solution. It would be lesser than 100 cm cube. The reason being some of the sugar particles are going to occupy the spaces between, okay, the spaces of the solvent particles, in this case water, and the net volume of the solution is going to be lesser than the sum of the volumes of the solutes and the solvent particles. It will always be lesser because the spaces between the solvent is where the particles or the solutes or some other particles are going to get inside, and therefore the total volume will be always lesser in solution compared to individual volumes. And that brings us to the end of the particulate nature of matter in terms of diffusion and dissolving. Hope you enjoyed the lesson. Till I see you next time. Bye-bye.